Good morning, everyone. My name is Swarnaker, and today I will be presenting my final project for Engineering 9857 course titled Design and Simulation of Bidirectional DC-DC Buck and Boost Controller for Electric Vehicle EV Charging System. This project focuses on designing and simulating a system that allows electric vehicle to both charge from the grid and discharge power back to it using a single converter and a smart control system. The main scope of this project was to build a bidirectional DC-DC converter system using a buck-boost topology. The goal was to enable both grid-to-vehicle and vehicle-to-grid power transfer in a stable and efficient manner. The system was modeled and simulated in MATLAB Simulink with a focus on control stability, voltage regulation, and battery state of charge tracking. A dual-loop control strategy was implemented for precise operation across both modes. As electric vehicles continues to grow in popularity, so does their impact on the electric grid. Traditional charging systems only support one-way charging, which limits their contribution to grid flexibility. However, bidirectional charging allows EVs to act as a mobile energy storage units, helping stabilize the grid during high demand periods. To achieve this, we need a smart converter that can manage power flow in both directions with, with appropriate control settings. In this project, I implemented both G2V and V2G concepts. In G2V modes, power flows from grid to the vehicles. It charges the battery of the vehicles. In V2G modes, the battery sends power back to the grid. These functions support peak shaving, voltage regulation, and integration with renewable energy systems. Bidirectional charging benefits both EV owner and grid operator, especially in future smart grid environment. It will be very much helpful. The buck-boost converter is central to our design. It supports both step-down and step-up voltage operation, making it ideal for EV application, whereas the battery voltage is lower than or varies with respect to the grid DC bus. In buck mode, it lowers 400 volt DC to the battery voltage, that is 160 volt, for charging operation. In boost mode, it raises battery voltage to 400 volt DC to feed back into the grid. This single converter enables efficient, compact, and cost-effective bidirectional power control for both grid-to-vehicle or vehicle-to-grid operation. Ensures safe, stable, and efficient operation of the bidirectional converter, this project implements a dual-loop control strategy, which is a standard yet powerful method in advanced power electronics. This structure consists of two feedback control loops, an outer voltage control loop, and an inner current control loop. The outer loop is responsible for regulating the DC link voltage, which is maintained at a constant 400 volts. It compares the measured DC voltage to a reference and generates a current reference as an output. This loop responds more slowly and maintains the desired voltage level despite load changes or mode switching. The inner loop, on the other hand, operates faster. It takes the current reference from the outer loop and ensures that the inductor current closely follows it. This loop provides accurate control of power flow, enabling a smooth transition between G2V and V2G modes. Both loops use proportional integral PI controllers, which are tuned to reduce steady-state error while maintaining system stability and responsiveness. Once the current command is generated, it is translated into PWM signal that controls the switching behavior of the converter. The switching frequency is set to 10,000 kHz for efficient operation. To enhance safety, and interlock logic mechanism is implemented. This ensures that both the high side and low side switches are not turned off simultaneously, which could otherwise lead to a short circuit across the power supply. Overall, this dual loop control strategy provides precise regulation, fast response, and reliable operation under both charging and discharging scenarios, making it ideal for real-world EV grid integration. Here's an overview of the system architecture. It includes a single-phase AC grid input, an active rectifier to produce a 400-volt DC link, a bidirectional buck boost converter, an EV battery with a nominal voltage of 160 volt. This system intelligently switches between charging and discharging mode based on control signal and user demands, and this structure forms the backbone of the simulation model. Now, this slide explains the control signal flow of the systems in grid to vehicle mode and vehicle to grid modes. Starting with the control signal flow, the outer PI controller continuously monitors the DC link voltage and compares it with a reference, typically set to 400 volt. It generates a reference current based on the error. This current reference is passed to the inner PI loop, which ensures that actual inductor current closely follows it. The output of the inner loop is fed into the PWM generator, which controls the switching of the converter MOSFETs. An interlock logic unit is shown included to prevent both high side and low side switches from conducting simultaneously, ensuring safe operation. This slide shows the energy flow path of our system. In GTV mode, energy flows from grid to rectifier, then to DC link, then to buck converter, and lastly to the battery. In other hand, in B2G mode, energy flows from battery to boost converter to the DC link to inverter and then to the grid. The full system was modeled in MATLAB Simulink software. It includes subsystem for the AC-DC rectifier, for DC link, for buck boost converter, and control logic. Separate control blocks handle the outer and inner PI loops, PWM generator, and mode selection. The model also tracks key variables such as current, voltage, battery shock throughout the simulation. In the G2V simulation, we set the reference current to minus 12 ampere for charging. The result shows the grid current and voltage are in phase, confirming energy is drawn from the grid to the battery. Battery current tracks the minus 12 ampere set point accurately. DC link voltage remains stable at 400 volt, and most importantly, state of charge of the battery increases gradually, indicating successful charging for this operation. Again, in the V2G simulation, we reverse the current reference to plus 12 ampere for discharging. The system behavior was grid current and voltage are out of phase, confirming reverse power flow. Battery current tracks the 12 ampere reference. The DC bus remains steady at 400 volt again, and for this time of operation, state of charge of battery decreases smoothly as energy is sent to the grid from the battery. In this slide, I would like to highlight the control performance and overall stability of the system during both G2V and V2G operation. First, the system control response was evaluated by observing how well the inductor current and DC link voltage followed their respective references. In both modes, the dual-loop PI controller architecture provided excellent performance. The inner current loop tracked the reference current, whether charging or discharging, with minimal delay or overshoot. This is especially important because accurate current tracking ensures proper energy flow and protect the battery from high current spikes. The outer voltage loop successfully regulated the DC link voltage at a steady 400 volt despite changes in load and direction of power flow. There were no significant fluctuation or voltage dips observed during mode transition, which demonstrated the robustness of the control system. Another key indicator of system stability is the voltage ripple on the DC bus. During simulation, this ripple remained very low, well within acceptable limit, indicating a well-tuned controller and effective energy buffering throughout the converter. Additionally, the transition between G2V and V2G modes was smooth and controlled, with no instability or distortion in current or voltage waveform. This reflects not just good control design, but also a successful implementation of PWM switches and interlock logic. Overall, the simulation result confirmed that system operation with high control accuracy, low error, and excellent dynamic stability, all of which are essential for real-world grid-integrated EV charging system. In this table, I compare system behavior in both modes. So for converter modes, in G2V mode, it was acting as a buck converter, and in V2G mode, it acts as a boost converter. Current direction is minus 12 ampere and plus 12 ampere for both for respective operation, and shock behavior is increasing and decreasing, while grid phase is for voltage and current is in phase for G2V mode, but for V2G mode, it is out of phase. The converter adjusts its behavior appropriately in each mode while keeping DC link stable. Here are the key outcomes of this project. It successfully implements a single converter system for bidirectional EV charging, developed a dual-loop PI control system for tight regulation of voltage and current, validates the system in both charging and discharging scenarios. The system can be expanded in the future to integrate renewable sources like solar PV. In conclusion, the project successfully demonstrates a grid-tied bidirectional EV charging system for both G2V and V2G operations, and those are tested for both operation and that found stable. The system maintained a 400 volt DC link and accurately tracked current and SOC of the battery. So my future work includes hardware implementation, integration with renewable energy sources, and testing under real-time load variation and applying advanced control strategies for everyday use. Thank you for your time and attention. I would like to express my gratitude to Dr. Mohsen Jamil for his support and guidance throughout this project. And again, thank you.